So just go ahead and get started then. Okay. All right. So yeah, we'll just get right into it. So Himali already introduced me, but so basically my experience is mostly with computer vision. I haven't done a lot of like robotics, which is what you're all into, but computer vision is obviously super important for robotics anyway, so you should get something out of this. So what we're going over today is event-based vision with dynamic vision sensors. So what are dynamic vision sensors? You might also see them under the name event-based cameras. But basically what they do is they capture changes in brightness asynchronously at each pixel. So if nothing changes, the sensor is completely dark. And the output of sensors is not images, but it's event streams. So basically, you'll have this kind of point cloud, which you can see on the bottom right-hand corner here, a kind of point cloud of the activations on the pixel array over time. So it'll be sort of a 3D point cloud where you have your XY, which is the kind of the image space, which you're used to, but then you also have time. So time would be your third dimension. So you get this kind of point cloud representation. And basically the kind of motivation behind these dynamic vision sensors is that they work more like how the human eye works. So like your eye doesn't actually see a constant image. It sees only the change in your image. As each sort of neuron in your eye fires asynchronously when it has a magnitude change or a color change that is interesting to it. So these sensors work by that same sort of basic principle. They only activate when they see something of interest, when it crosses some threshold that's appropriate, which is tunable. So what are some characteristics of these sensors? They have extremely low latency. So they have megahertz scale sampling. So you're taking an event about once every microsecond. And some of them are even faster now too. And they have very high dynamic range. So you have 140 decibels versus 60 dB. And dynamic range being obviously, not obviously, but the kind of the minute change in luminance that the pixel is capable of detecting. So a regular camera might not see any change, whereas the event-based sensor is way more sensitive and might fire events. And then also these are very, very low power. So you're in the milliwatt range versus the watt range for most sensors and cameras. Okay, so why are they useful? For one, because you have this really high sampling rate, you have no motion blur, virtually no motion blur. And because they're also very insensitive to many light saturating scenarios. So because they're only looking at change, you don't have something like this situation in the bottom right-hand corner here, like glare. Actually, autonomous driving is something that the event-based sensors there's a lot of research going on in that. And this is one of the things they're worried about. So kind of like light conditions, it's completely agnostic to any light condition because it just focuses on the change. And then another thing, which actually I did in some of my previous work, is high brightness scenarios with astronomy. So kind of like whenever you do telescope imaging around the moon, it's called cislunar imaging. The moon is extremely bright. It's way brighter than any star around it. It's way brighter than satellites. So it's actually very difficult to image satellites near the moon. And a lot of research is going into how they might do that with these event-based sensors. And also another thing is very low data rate because you're asynchronously sampling, right? You're not taking every single pixel output at every microsecond. You're only taking some smattering. So compared to a camera of the similar sampling rate, it has much, much lower data rate. So here's actually a kind of a depiction of where it might be useful in autonomous driving. Because you have this high dynamic range, you can image under very, very low light conditions. So on the left-hand side, you have a regular camera. You can barely see anything. But on the right-hand side, you have the event-based camera. It's only firing these little changes in the brightness along the image. So you can actually see fairly clearly things that are completely invisible in the regular camera. And one thing to note, so like how these work, we're going to be getting into how these work actually. So yeah, another instance of why they're useful, comparing it to an equivalent conventional camera, right? So this is like a high frame rate camera. You might do like, 4K high speed imaging, up to 1 megahertz, resolution, very poor, weight, 6.2 kilograms. It's really heavy. I mean, you see this giant box. Data rate, 1.5 gigabytes per second. So gigabytes per second. So if you take a couple of minutes of video with this high-speed camera, you're filling up everything. And then power consumption, the high-speed camera is 150 watts versus the event camera is, 1 milliwatt. Yeah, and they require active cooling because they get really hot. So very unwieldy. So event cameras have a lot of benefits, a lot of advantages here. So how do they actually work? So unfortunately, this is in the way. Let's move this. So this is kind of just a very, very high level schematic of how an individual pixel on the event camera works. Basically, you have some sensitive photoreceptor, a photodiode, and then what it's going to do is it's going to accumulate a log of luminance of this. You have a capacitor here. I don't know how many people have been familiar with this. But yeah, so what it does is it's going to take a difference at every time step. So it has, its megahertz sampling rate. It's going to take a log scale difference, and it has two thresholds. So it has like an on threshold and an off threshold. So if it drops by an on amount, or if it raises by an on amount, it will fire off a positive polarity event. And then if it drops by, whatever the off threshold is, and they don't have to be symmetric, they can be tuned for different, scenarios, different use cases. But then you'd fire an off event. So this graphic here kind of illustrates that. This would be on the y-axis, the log of luminance of whatever the photoreceptor is receiving. So then whenever you have an increase by a certain amount, you're going to fire this on event. And then when you drop, you're going to have these off events. So actually, there are some variations of this. There's some newer models of the event-based sensor. So this is what's called an ADIS pixel. So this is a kind of it basically has like two sensor schemes in parallel. You have the regular event-based sensor, so you can see has the illumination curve, it's firing off events, and then you have on the right-hand side the picture of the Eiffel Tower, all the different events. But then you also have an exposure measurement. So what you can do is you can actually integrate over all those events. It has some pulse width modulation there, and then you can actually create a grayscale image from it. So this way you get, you have your kind of classical image format, and then you have the event stream, the 3D point cloud format. So what can they do? What can you do with this? So high-speed collision avoidance in UAVs. These are actually from my previous works. So what this is Microsoft has a simulation environment called AirSim, if anyone's familiar with it. We're doing kind of like UAV, navigation, collision avoidance. And they also run like a race. It's a competition, so you can run a race. So this was actually, this is from the AirSim environment, which is just an Unreal Engine. And then usually they run a race, but what we were doing was doing high-speed collision avoidance, and we trained a spiking neural network. So actually, spiking neural networks are used a lot with event-based sensors because spiking neural networks are asynchronous, just like the event-based sensor. So basically, you can have a spiking neural network layer and feed in this event stream without making a lot of modifications. They kind of just naturally complement each other. So what we did was we trained a spiking neural network with reinforcement learning, deep Q learning, with a simulator that we built. So this was actually a simulation of the event-based sensor within the AirSim simulator. So you can see like that's kind of like it's a rough approximation of what an actual event-based sensor would see. But we trained that, and we ran through and did a lot of high-speed collision avoidance. It worked well. And then the bottom here, this is what I was mentioning before, where you have very, very dim satellites and extremely noisy telescope imagery. So you can pick them out. It's still very difficult to see even with the event-based sensor, but it's visible versus where in the regular CCD camera, it's not visible at all. Yeah.
Your collision avoidance,
Yeah.
Did you test it on the same environments you trained it on? I'm assuming, yeah.
No. I mean, we obviously, we tested it on the same environments, but actually what we did is we built like a separate, like, we had like lanes set up with like different kind of just geometrical obstacles that we set up. So we had so basically we controlled the type of obstacles it was encountering. And then we trained it like going down each of these lanes, and we benchmarked it across some different, methods. Yeah.
So like the disadvantage compared to RGB camera would be that you don't get to build a 3D point out of the actual world. So then you do that's it.
Say that again?
It's like, so like if you have a RGB camera, you
Yeah.
can actually get a 3D representation of the environment.
Yeah.
And plan around obstacles.
Mhm.
But in your case, I'm just trying to like understand the disadvantages of it. Because,
The disadvantages of the event-based sensor?
yeah, because for your case, you have to do direct sensing to actions.
Yeah. Well, I mean, of course you could do planning. I mean, there's tons of research out there and they do all kinds of mapping with the event-based sensors too. So this was just our approach. Um,
How would you be planning?
hmm?
How would you be planning this to figure?
Well, no, yeah. What?
No,
Okay. No, yeah.
so when you want to use planning, you have to start.
No, you don't have to. I mean, we'll see that later, but they have algorithms for doing it with the event-based sensor, and also you can reconstruct regular frames. So you can like reconstruct regular frames and do it over a sequence, you know.
You capture that.
There's some extrapolations, yeah. Yeah, they have ways of estimating it, yeah. So here was just another cool thing that they can do. You don't have to watch the whole thing, but so this is doing frame interpolation. So what they do, they have a regular camera and then an event-based sensor in parallel with it. So they have some this kind of low frame rate video input, and then they're speeding it up just by interpolating the frames from the event-based data. Yeah. And they have some, yeah, they're kind of showing how it's done. So you see, like, this is how the event-based camera kind of collects data. You see it's like this evolving stream when you see the images in parallel. And the positive polarity is an on event, so that's when it's an increase in brightness, and the negative polarity is an off event, so when whenever it's losing brightness. Yeah, so this is a kind of like a low cost way. If you had some, cheap event-based camera in parallel with your regular camera, you could get, high speed regular imagery by doing this reconstruction process. So how about robotics, which is what you all care about, right? So here's actually this pretty cool robot here. So they're doing this like ball catching, obviously with an event-based camera. I think they show how it's yeah, so this is the view from the event-based camera on the robot. And they have it all in simulation as well. So yeah, and then there's also another obstacle avoidance with UAVs. So this is actually, let's see if we can load this up a little bit. I guess we can't. But anyway, you can see how it's the event-based camera in the upper right-hand corner here as it's like moving around really kind of haphazardly. It's making these fast kind of collision avoidance decisions. And also you can see like the sort of the edges of the room are what you get most of the events from. And this is the kind of the event-based representation of that. Yeah, so that's cool. Yeah.
So, they can't do that with a normal camera? Like, what is, that is cameras that much faster?
It's that much faster, yeah. Yeah. I mean, we're talking like, it's on the megahertz scale, so like a million frames per second, not frames per second, obviously, but yeah.
Compared to the baseline with a normal camera.
Right. Yeah. Well, I mean, it can do it, obviously, but more slowly. Yeah.
These two methods, do they use spiking neural networks or they use something?
I don't think this is a spiking neural. No, I don't think either of these are spiking neural networks. Yeah, you can use, yeah, there's a bunch of regular algorithms too. what people sold to. Okay, so how do you actually use these? There are some issues with this. Very low resolution for entry-level cameras. The higher resolution ones are extremely expensive. And the data is asynchronous, so you can't just run regular object detection algorithms on these because they're not images. But there are some options you have. So ETH Zurich has a whole research group completely dedicated to these event-based sensors. And they have a really great repository for doing basically anything you can imagine with them. And another thing is they have a DBS simulator. So you can actually generate event-based data just from regular videos and then experiment around with algorithms and everything. And then you can also actually so you take regular videos, you can convert them into event-based representation. And then you can do the opposite as well. So they have very high-speed reconstruction, which is kind of like the same thing that we just saw in that other video. But once you reconstruct images from the event-based sensor, then you can run regular algorithms over it. So now, obviously, maybe you could do that with a regular camera because, there's going to be some latency with the reconstruction process. But hypothetically, if you could reconstruct it fast enough and run that algorithm, you still might be beating out a regular camera. And it has full ROS support. I think Innovation, the one company that makes these, has a full managed package that they have. I don't have a lot of experience with that, but yeah, it's all available. So yeah. So anyone have any questions? Yeah.
When you say it's asynchronous, does that mean the data isn't like real time? Like you can't detect data. Like,
Oh, okay. Yeah, so asynchronous is for the pixel array, right? So and instead like a regular camera is synchronous because you take the whole image out from every single pixel. Asynchronous just means you're getting data from like some pixels on the sensor. You're not getting like a full camera image every microsecond.
data, some of the data is real time, but not all of it.
No, it's all real time. Yeah.
So that's how you were able to catch the ball.
Hmm?
That's how like you were able to.
Yeah, it's all real time. Obviously, if there's some reconstruction process going on, that's not real time. So like if you go to these sensors, like you're gonna have the event-based representation is real time, but then you have the pulse width modulation is giving you some grayscale regular image that's not going to be real time. Yeah. You see nothing. Yeah. You see absolutely nothing. Yeah.
They're not channel, so it's the brightness, they're not really channel, they're not like
Channel.
hard.
Oh, okay. So there are channel-based ones now. So I think it's kind of recent, but they have full color versions now. So yeah.
Able to detect the intensity of the change in, or like if they detect change in intensity of brightness, but can you detect a bigger change versus smaller change, or does it all of it the same?
No, the events are binary. Yeah. So you don't get any kind of continuous value from it. It's just an on or an off. And obviously you can tune those thresholds. But yeah, no continuous information. Yeah, it's going to be a different event per channel, right? So it's like, so instead of just 2 events, you can get what, 6 then? If you have like 3 channels that both have on and off events. So yeah. Any other questions? No. Back over. Yeah. Yeah. Okay. Somebody was waiting there. Yeah, I don't think anybody online is talking. But yeah,
Honey, do you have questions on that?
I don't think they can hear you.
Might be good.
I think you imagine.
No, it was not muted.
Or,
They can hear all of them.
Yeah,
There is something. There's many things in chat.
First color is blue.
Can anyone hear the voice? Nope. I can't hear anything. Can you hear now? Because audio is going off, so. Yeah, they can hear you. Okay. Yeah, okay. Well, I guess first meeting, so, you can work out the kinks, so. We're getting some thumbs up, yeah. Yeah, so,
I'm saying.
okay. Yeah. Did you not have anything? They don't like do anything else?
No.
No?
Wait, did you stop? Oh.
I didn't, no.